Now let's talk about p-hacking, which is the second way in which researchers can fool themselves about their results, often without knowing they're doing so. Now, to understand this, we have to go a little bit into the statistics. Now, normally all analyses will have noise of some description. That might be lab noise for an physics experiment, or it might be statistical noise for doing a psychology sample or a medical clinical trial or something like this. And this noise is normally assumed to follow a normal or Gaussian distribution. And that means the result that you get is not the true result. It'll be different by some amount that depends on how noisy, how much uncertainty there is in your experiment. And this is inevitable in almost all experiments. Now, what people normally say is that to be able to claim that you've discovered something, your result has to be statistically significant. And this is a very widely misunderstood term. In the social sciences, normally to publish something or to claim that you've discovered a result, you'd have to say that it's reached 95% statistical significance. It's a p-value of 0.05. Now that sounds good, we're 95% confident this is correct, but that's not what the statistic actually means. The statistic is actually the odds of rejecting the null hypothesis. So it's not saying if something has a p-value of 0.05, 95% confident, that doesn't mean you can be 95% confident it's right. What it means is that if this result was not right, the null hypothesis, there's no more than a 5% chance of you getting data as extreme as what you actually see. So let's say, for example, you're trying to do a survey to see whether eating chocolate makes people run faster. Your null hypothesis might be that eating chocolate does not make people run faster. You might set two bunches of people running and time them, some of whom have had chocolate, the other group has not had chocolate, and see which group are faster. But there's going to be some randomness anyway, because you're going to have randomly faster or slower people in the different groups irrespective. So if you could say it with 95% confidence, that means that if actually there was no difference between the two groups, there's only a 5% chance that just at random one group would run this much faster than the other group. So that's a rather subtle point. What it means is that even if everything is fair and well organized in your sample, if you're using 2 sigma, which is 95% confidence, a p-value of 0.05 as your threshold for claiming a result, you'd expect about 1 in 20 results to be spurious. People would have looked for something and just because of random fluctuations they would say, oh yes, we found this. That doesn't sound too bad. Sort of 1 out of every 20 papers is actually not significant. But it gets much worse than that. Let's imagine you do your study, you're trying to see whether chocolate makes people run faster, and you do the statistics and you come up with p of 0.07. Now that means if you publish this, you're going to say, well, we haven't really established that chocolate makes you run faster. It's looking suggestive, but we need more data, la-di-da, la-di-da. You might not even bother publishing. If you do, it's going to be a very weak paper. No one's going to cite something saying, well, you don't quite know what's going on here. Whereas if you can say p is 0.05, you can say, we have shown with 95% confidence that chocolate makes you run faster. So let's imagine you did get 0.07. You're going to be under a lot of temptation to think, maybe we can use a different statistical technique. Maybe we can use the Kolmogorov-Smirnov test rather than the Spearman's rank correlation coefficient. We had one very discrepant point. Maybe we throw that out. Maybe that person was ill or something on the day. Maybe we should go back and calibrate our data again one more time, or maybe we need a bigger sample. And you might keep on tweaking these things until you get it from 0.07 down to 0.05, at which point you can stop and say, yep, okay, significant, I'll go and publish it, it's going to be a good paper, now people are going to cite me, I'm going to get a job. And we can see this happens because if you look at how many results have a p of 0.05, 0.04, 0.03, 0.02, etc., etc., we find a big spike at just under 0.05. People have somehow just managed to get it over the hurdle. Now this is much less a problem in physics and astrophysics because we normally require a result to be 5 sigma. That's p of 0.000006 to consider it significant. So for example, at the Large Hadron Collider they didn't report report the discovery of the Higgs boson until they'd done enough stats to report it at the 5 sigma level. That makes it far less of a problem. But if you really are, I can understand why social scientists and psychology and medicine often use 0.05 because their samples are big and time consuming. If you need to have another 10,000 people taking a drug to measure something, that's very costly and very time consuming. So you want the smallest sample you can to get one with reasonable confidence. Another variant of this is what's called harking, hypothesis after results known, HARK. The idea is you do your experiment and it doesn't give you the answer you want, but maybe you start playing with the data to see if there's something else you can find in there that does give you a statistically significant answer that's going to make your paper look good. So for example, let's say you're trying to study whether multiple choice tests disadvantage female students, which is an actual result in the education literature. And let's say you take a whole bunch of students and give them multiple choice tests and the women do worse. But it's not statistically significant, it's a p of 0.08 or 0.2 or something like that. So it's going to be a really boring paper. We tried to see whether this happened and our results were inconclusive. We couldn't prove anything. Maybe it's suggestive, la-di-da. No one's going to cite that. It's not going to help your reputation at all. But maybe you start looking at the data and saying, well, sure, I couldn't see a difference between the female and male students. But how about if you look at the female students of colour? So students have the double disadvantage of being both female in a science course and from an ethnic minority. Oh no, that didn't give an answer either. Okay, maybe it only disadvantages female students in subjects which are male dominated, like physics and engineering, but not in things like history. Oh, still not seeing anything there. But the basic idea is if you don't see one result, you can keep looking for another and another and another. And if you look at enough, you're eventually going to find something that's significant at this 0.05 level. On average, you need to look at about 20 results to find one that's 5% significant. So you might say, yes, we find this result of 0.05% significant, but if you looked at 20 different results, you'd expect that. It tells you nothing. It just meant you kept looking until you found what you were after. Infamous example was Professor Brian Wansink, head of Cornell's University Food and Brand Lab, head of the US Nutrition Program for a number of years. Very high-profile person, famous for his really cool experiments, published hundreds of high-profile papers, absolute top of the nutrition game. Now he showed, for example, which you may have read about, that having a large plate at a buffet makes you eat more, so you should have a small plate so you'd eat less. He also showed that if you go shopping when you're hungry, you'll buy more food. So you should always make sure you shop after a meal, not before it, if you want to lose weight. Now, he was prestigious, high reputation, until he destroyed his own reputation by posting a blog post himself about how he encouraged one of his graduate students to get good research from data on a New York pizza restaurant. They've got a whole bunch of restaurants at this pizza restaurant. And he said in his blog post, look, the original hypothesis had failed. We were trying to test a particular thing. I don't know what it was, but it didn't come out right. But he told his student, look, we want to make you more productive here. We want to get you a job. There's got to be something here we can salvage. Maybe look at other things. The graduate student came back every day with puzzling new results and every day came up with another way to reanalyze the data. So he had inadvertently revealed, presumably because he didn't see there was anything wrong with this, that he was doing big-time p-hacking. If you didn't get the exciting result, you keep looking, you play with the data this way, you correlate different things, you play with a different statistical technique, you keep on playing until you get that magic 0.05, and then you can publish an exciting paper. In this case, he was trying to help his graduate student get an exciting paper, but he destroyed his own reputation, his own career in the whole process.